You know, our whole world is built on pipes and vessels under pressure. You see them everywhere, from giant chemical plants to the power stations that light up our cities. But what's the one thing, the one crucial check that stops them from, well, failing catastrophically?
Let's just cut right to it. What single safety check stops a massive refinery from blowing up? The answer is this high-stakes test that happens all the time, just totally out of sight.
It's called a pressure test, and it's something that has to be done every single time a piece of equipment is built or repaired or even just slightly altered. It's all about making sure it's safe.
I mean, think about it. You put in a new weld, you replace a valve. Any little change introduces a potential weak spot. So that piece of equipment, it suddenly has this invisible question mark hanging right over it. Is it strong enough? Is it sealed up tight? A pressure test is how engineers find out the answer before it's way too late.
So what is it really? Well, a pressure test is basically a controlled procedure to prove one thing, that the system is structurally sound and it is not going to leak. You can think of it like the final exam a piece of equipment has to pass before it's allowed to start its job.
Now, engineers have two main ways to do this test. They can use water, which is called a hydrostatic test, or they can use air in a pneumatic test. And believe me, the choice between them has absolutely enormous consequences.
And here is the fundamental trade-off. Water is incompressible. That means if something goes wrong, the pressure just drops instantly, and all you get is a leak. It's super safe, but yeah, the cleanup can be a real pain. Air, on the other hand, is a compressible gas. It's really easy to clean up. It's just air. But if something fails, that compressed gas expands violently. A simple leak becomes a dangerous rupture. An inconvenience becomes a potential disaster. Here's a good way to think about it. A hydrostatic test is kind of like filling up a water balloon. If you hit a weak spot, what happens? It springs a leak, water squirts out, and boom, the pressure is gone. Sure, it's messy, but nobody gets hurt. But a pneumatic test? That's more like overinflating a massive truck tire. When that thing fails, it doesn't just leak, it explodes. It releases all that stored up energy in one huge, dangerous blast. That's the risk engineers are desperately trying to avoid. And hey, don't just take my word for it. The official engineering standard, ASME PCC2, says it right there in black and white. The energy in that compressed gas makes pneumatic testing potentially much more hazardous. So, why would anyone ever choose it? I mean, given the choice between a safe leak and a dangerous explosion, the decision seems pretty obvious, right? But the thing is, sometimes using water just isn't an option. And in those cases, engineers have to navigate that choice using a really strict logical process. They actually follow a decision-making flowchart that looks something like this. Now, don't worry about reading every single box here. The main point is that this isn't guesswork. It's a super rigorous safety roadmap, and there is absolutely zero room for error. In fact, we can boil that entire complex map down to three basic questions. First, can the equipment and its supports even hold the immense weight of all that water? Sometimes the answer is no. Second, will the water contaminate the final product or maybe even corrode the equipment itself? And only if they're forced to, only then do they move to the third and most critical question. Can we manage the extreme risks of using air? And this brings us to the most critical calculation of all. If an engineer is forced to use a pneumatic test, they have to quantify the danger. They have to calculate the exact explosive potential of all that energy stored in the compressed air. It all comes down to this idea of stored energy. See, a compressed gas is like a tightly coiled spring just waiting to be released. It's holding a massive amount of potential energy. A failure unleashes all of it, all at once. And engineers have a way to measure that force in a unit we can all understand. So let's take a pretty common test pressure, 500 psi. Seems like just a number, right? But what does that actually mean in terms of danger? Well, using the formulas right out of the engineering standard, that pressure inside that vessel is equal to the explosive force of 10 kilograms of TNT. No, that's not an analogy. That is a direct energy equivalent. Suddenly, the potential for a catastrophic failure isn't some abstract idea anymore. It's a bomb. So, what do engineers do with that terrifying piece of information? They establish a blast radius. For a blast that's equivalent to 10 kilograms of TNT, the standards say you need a minimum safe distance of 70 meters. That is nearly the length of a football field that has to be completely cleared just to protect people from flying shrapnel.
And that's because within that radius, the consequences are just devastating. A blast wave from a pneumatic test failure can shatter windows, it can crumble concrete block walls, and it can completely collapse brick structures. The fragments of the vessel itself become lethal projectiles. The stakes just don't get any higher.
Okay, so let's just pull about for a second here. All of these calculations, these choices between water and air, these blast radiuses, this is the invisible engineering that underpins the safety of our entire modern world.
So the next time you drive past a big chemical plant or a refinery, just remember that it's protected by more than just steel and welds. It is secured by this incredibly rigorous process, a silent guardian working behind the scenes to make sure the worst-case scenario never happens.
And really, in the end, it all comes back to this one simple, powerful statement from the standard itself. The whole goal, the primary purpose, is to verify integrity. It's all about turning that question mark on a piece of equipment into a definitive exclamation point of safety.
It really makes you wonder, doesn't it? As you go about your day, what other invisible calculations, what other silent guardians are working all around you right now to keep our complex world from falling apart? Thanks for joining me for this explainer.